All right, so today we're diving into sodium superionic conductors.
Yeah.
You've sent over a bunch of research on this, including a really interesting paper from Nature Communications.
Yeah.
And these materials, they seem like they could be really key to unlocking the potential of solid-state sodium batteries,
Right.
which, as we all know, are kind of a promising alternative to the lithium-ion batteries we've all come to know and love. So let's explore a bit about, why these sodium superionic conductors are generating so much excitement and what the latest research says about how to actually design these things.
Yeah, it is really fascinating to see how this quest for better energy storage is driving so much research.
Yeah,
And, lithium-ion batteries have served us pretty well, but
Yeah.
they have some limitations,
for sure.
especially when we start thinking about large-scale things.
Right.
Like grids,
Exactly.
electric vehicles.
Yeah, plus, lithium is expensive
Oh, yeah.
and a finite resource.
And the price fluctuates.
Yeah, exactly. And then, safety is always a concern with those liquid electrolytes in our conventional batteries.
Yeah, no kidding. I mean, that's a huge factor that's driving people to look for alternatives.
Right.
And that's where sodium comes in. It's abundant, it's inexpensive, and it offers that potential for safer solid-state batteries.
Right.
But to make those batteries a reality, we need efficient ion conductors.
Okay.
And that's the tough part.
So that's where these sodium superionic conductors come in.
Exactly. So for a solid-state battery to work, you need those ions to move through that solid electrolyte material quickly.
Right.
And that's what superionic conductors are good at.
Okay, so that makes sense.
Yeah.
But why are sodium superionic conductors so tricky to design? I mean, we've already made so much progress on lithium superionic conductors.
Right.
Why can't we just, use those same principles for sodium?
Oh, if only it were that easy.
Okay.
The problem is sodium ions are different from lithium ions. They're larger and they're a bit more picky about where they are in the crystal structure.
Okay.
They want to be in sites with higher coordination numbers, meaning they like to have more anions nearby.
So it's like they need more room?
Yeah, more elbow room.
Yeah.
And because of that size and that preference for higher coordination, sodium ions don't move through the material the same way that lithium ions do.
Okay.
Their paths are different.
Right.
And the energy barriers that they encounter are different.
Okay.
So yeah, basically just mimicking those lithium superionic conductor designs
Right.
just won't work for sodium.
Okay, so we need a whole new approach then.
We need new rules.
Yeah. Okay.
And luckily, this Nature Communications paper really digs into that.
Okay.
They found a really key principle for creating those efficient pathways.
Okay.
It's called phase-sharing high coordination sites.
Okay. Phase-sharing high coordination sites. You're going to have to break that down for me.
Okay, sure. So imagine a sodium ion
Okay.
moving through a channel within the material.
Okay.
Now, this channel, it's not just like a tunnel.
Right.
It's made up of individual sites.
Okay.
Where the sodium ion can hang out for a bit.
Right.
Kind of like rooms all connected.
Okay, so each room's like a potential stopping point for the ion as it's going through.
Exactly. And we want those rooms to be those high coordination sites that the sodium ions like.
Okay.
But here's the important part.
Yeah.
These high coordination sites need to share a face.
Okay.
Like two rooms that share a wall.
Okay.
With a nice big doorway between them.
Oh, so it's not like they're squeezing through some tiny little space. They have like a big open area to move through.
Exactly.
Okay.
And that arrangement makes sure that those sodium ions can hop directly between those comfy, spacious sites.
Okay.
Without running into any, energetically unfavorable bottlenecks.
I see. So it's all about creating a smooth, spacious highway for those sodium ions.
Exactly.
Okay. But why is this phase sharing so important for sodium, but not really for lithium?
Oh, that's a great question.
Lithium ions are smaller.
Yeah.
Right? Wouldn't they benefit from these wider pathways too?
So lithium ions don't mind those smaller doorways as much.
Oh, okay.
They're more agile.
Right.
They can get through those tight spaces without much of an energy penalty.
Okay.
It's like designing doorways for different sized dogs.
Okay.
A small dog can slip right through a narrow opening.
Right.
But a big dog needs a much wider door to get through.
That makes sense.
Yeah. So for lithium, phase sharing is not so important.
Okay.
Because their preferred sites are already pretty small.
Right.
And connected.
But for those sodium ions,
yeah,
they need those phase-sharing high coordination sites.
they need that open path.
Yeah, to have that smooth pathway.
Exactly.
All right.
I got it.
Cool. It's all about matching that architecture to the ion.
Yeah.
And
right.
So this paper is really a breakthrough
Yeah.
for sodium superionic conductors.
Yeah.
It gives us that blueprint to design those materials that can make those solid-state sodium batteries a reality. Okay, so we have this blueprint now, this design principle, to create those efficient sodium-ion pathways.
Right.
But the researchers didn't stop there.
Right. No, they didn't just stop at the theory.
They put it to the test.
They did. They
Yeah.
used it to run this huge computational screening,
Okay.
like a giant virtual experiment,
Wow.
to find new sodium superionic conductors.
So they were looking through like a massive database of materials
Yeah,
to find ones with the right structures for fast sodium-ion conduction.
exactly.
Okay.
And they found some pretty amazing stuff.
Like what?
Well, they identified over a dozen potential sodium superionic conductors.
Wow.
And they had all sorts of compositions like oxides, sulfides, even chlorides.
Wow. A whole new family of candidates.
Yeah.
Were there any that stood out?
Oh, yeah, absolutely.
Oh.
One was this new family of chloride-based conductors.
Okay.
They had a formula of NaCl6,
Okay.
where M can be something like lanthanum or samarium.
Fluoride-based conductors. That's interesting. You don't hear about those that often.
Yeah, usually it's oxides or sulfides for solid-state electrolytes.
Right.
But this research shows that maybe these halide-based conductors have some potential.
Okay.
And one of them,
Yeah.
this NALA 0.95Te 0.43 Cl6,
Okay.
it had a room temperature ionic conductivity of 1.4 MScmu.
1.4 MScmu.
Yeah,
Okay, so for those of us who don't speak ionic conductivity,
sure.
what does that number actually tell us?
That's a great number,
Okay.
especially for a halide-based sodium-ion conductor.
Okay.
I mean, it's way higher than anything reported before for these materials.
Oh, wow.
And, higher conductivity means faster ion transport,
Right.
which means faster charging and discharging.
Oh, so this chloride conductor could actually lead to batteries that charge way faster
Yeah, exactly.
than what we're used to.
It's a game changer.
Yeah, that's a big deal.
It really validates that phase-sharing design principle,
Right.
It shows that we can actually get those big improvements in sodium-ion conductivity if we tailor the structure of the material.
So it's like they figured out the secret
Yeah,
to designing these efficient sodium superionic conductors.
exactly.
But we've been talking about batteries a lot here.
Right.
You mentioned that superionic conductors are important for other energy technologies too, right?
That's right.
Like what?
Well, fuel cells, for example,
Okay.
they can be really important there.
Remind me how fuel cells work again.
Well, basically, a fuel cell takes chemical energy
Yeah.
and converts it directly into electrical energy.
Right.
So you have a fuel like hydrogen
Okay.
and an oxidant like oxygen.
Right.
And they react electrochemically
Yeah.
to generate electricity.
Right, I remember that.
And the superionic conductor,
Yeah.
it acts as a solid electrolyte in there. So it
Okay.
helps move the ions between those electrodes,
Right.
which is essential for the fuel cell to actually work.
So it's like the bridge that lets those ions flow
Exactly.
to complete the circuit so that energy conversion can happen.
A perfect analogy.
Cool.
And, just like with batteries, the efficiency of a fuel cell depends on how well that electrolyte conducts.
Right.
So these high-performance superionic conductors,
Yeah.
whether they're lithium or sodium,
Right.
they can really impact a lot of different clean energy technologies.
So it's all connected.
It is.
A breakthrough in one area can lead to new innovations in other areas.
Absolutely.
It really shows how important that fundamental research is.
Yeah.
Exploring new materials, even if we don't know what they'll be used for yet.
Yeah, sometimes the best discoveries come from the most unexpected places.
Right.
And this research on sodium superionic conductors is a perfect example.
Yeah.
It started with a basic question,
Yeah.
How do we design these materials
Right.
to move ions efficiently?
Yeah.
And now it's opened up all these possibilities for
Yeah.
new energy storage and conversion technologies.
It's amazing to think that just the way atoms are arranged in a material can have such a big impact
It is.
on the future of energy.
It's really just the beginning, too.
Yeah.
There's so much more to learn in this field.
Okay, so we've been really excited about these sodium superionic conductors,
Right.
but let's be realistic here.
Okay.
What are some of the challenges that are still in the way
Yeah.
before we see these solid-state sodium batteries powering our devices?
Well, that's a great question, and every new technology has those challenges,
Yeah.
before it can be commercialized.
Right.
And for these sodium batteries, one of the biggest hurdles is stability.
Stability, so like making sure they can actually handle real-world conditions.
Exactly. Some of them can be pretty sensitive to things like air and moisture.
Oh, so they can degrade over time.
Yeah, their performance can go down.
Okay.
So researchers are looking for ways to make them tougher.
Right.
Trying different compositions,
Yeah.
trying protective coatings to improve their stability and how long they last.
So it's not just about finding materials that conduct those ions well.
Right.
It's also about making sure they can last,
Yeah.
even if the conditions aren't perfect.
We need materials that can go the distance.
Right.
And another challenge is finding the right materials for the electrodes.
Oh, right. So it's not just about the electrolyte.
Yeah, the whole battery system has to work together.
Right.
The electrodes can really impact how the battery performs.
Okay.
The energy density, the charging and discharging rates,
Yeah.
even the lifespan.
Right.
So researchers are looking at all kinds of materials,
Right.
trying to find the perfect match.
It's like a dance.
Yeah,
Finding the right partners to make a battery that's efficient and long-lasting.
exactly.
Okay.
And then there's the question of scale.
Okay.
Even if we have the materials and the designs,
Yeah.
can we actually make these batteries on a large scale?
Yeah. And can we make them in a way that's affordable?
Right? We can't just stay in the lab. We need to be able to mass produce them
Exactly.
if we want them to actually make a difference in the real world.
For sure.
And that takes a lot of collaboration
Yeah.
between scientists and engineers and industry partners
Right.
to figure out the best way to make them
Right.
and make sure they can be made efficiently and affordably.
So it's not a simple challenge.
It's not easy.
It takes a lot of innovation
Yeah.
in material science, but also engineering and manufacturing.
It's a tall order,
Yeah, it is.
but the rewards are huge
Yeah.
if we can do this.
Right.
These solid-state sodium batteries could totally change how we use and store energy.
Yeah, it's pretty amazing to imagine, a world
Yeah.
powered by these safer, more sustainable, and potentially even more powerful batteries.
Right.
It feels like we're on the edge of a whole energy storage revolution.
It really does. And this paper shows just how fast things are moving in this field.
Yeah.
I mean, research on these sodium superionic conductors is pretty new
Right.
compared to the lithium ones. But we're already seeing so much progress.
It's like this whole new area of materials science is opening up right in front of us.
It is.
But let's take a step back for a second.
Okay.
We've been talking about all this amazing technology.
Right.
But there's also that sustainability angle here.
Oh, absolutely.
Using sodium instead of lithium.
It's a huge advantage.
Yeah.
Sodium is just so much more abundant.
Right, and readily available.
Yeah, exactly. And lithium has all those
Yeah.
geopolitical and environmental concerns.
Right.
So moving to sodium could really change how we power the world.
It's about making a more resilient energy future, right?
Yeah,
One where we're not all relying on just one resource.
exactly. And it just shows how important it is
Yeah.
to look for those alternative materials
Yeah.
and technologies.
Right.
We need to think outside the box,
Right.
challenge those old ways of doing things.
Push the boundaries.
Yeah, and really try to make that vision a reality.
And for all those listeners out there who are working on this stuff,
Yeah,
this is a call to action.
absolutely.
There's so much more to do in this field.
This paper's a great start.
Yeah.
It gives us that design principle for these sodium superionic conductors,
All right.
and it proves that it works,
Right.
but there's still so much more to do.
So where do we go from here then?
Right.
If these sodium superionic conductors are so promising,
Yeah.
what are the things holding us back
Yeah.
from seeing them in our devices?
That's the big question, isn't it?
What kind of new innovations in battery design
Yeah.
or material synthesis do we need
Right.
to really unlock their full potential?
Those are the questions we need to answer.
Yeah.
We need to dig deeper into how the structure of these materials affects their properties.
Right.
How can we tweak their composition
Yeah.
to make them even better?
To get better conductivity and stability.
Exactly. And are there new ways to make these materials
Yeah.
that will give them even better properties?
And how do we take all this from the lab
Right.
and scale it up
Yeah.
so we can actually manufacture these batteries
Right.
efficiently and affordably?
It's a big challenge.
Yeah.
It takes experts from all different fields,
Yeah.
materials, science, chemistry, engineering, manufacturing.
Working together.
Yeah, to come up with new ideas.
So for everyone listening to our deep dive today,
Yeah.
remember this.
Okay.
The future of energy storage
Yeah.
is being invented right
Yeah.
now
It is.
in labs and research centers.
all over the world.
Yeah, and with materials like these sodium superionic conductors
Right.
leading the way, the possibilities are pretty amazing.
They really are.